Okay, guys, today we're going to talk about solutions. So I've got some pictures up on this slide that remind me of solutions. So I bet when you thought you were going to take chemistry, you might have thought about solutions, different colored solutions and these fancy flasks and everything. Today what we're going to do is learn about solutions, so the different parts of the solution. We're also going to talk about how to measure the concentration of a solution. And so I hope that you have your Chapter 9 guided notes out and be following along. There's a lot of stuff to write down today. So let's get started. Let's start off with a definition of solution. And here it is. You're supposed to write this down. So while you're writing it down, I'm going to talk about it. So solutions are homogeneous mixtures that contain two or more substances called a solute and a solvent. So important to understand, there's two parts of a solution. One is called the solute and one is called the solvent. You've got to have a solute and you've got to have a solvent. But there's more to it than that. It says that solutions are homogeneous mixtures. Homogeneous, this prefix homo means same. Okay, so it just means the same. So a solution is a homogeneous mixture. So when you mix two things together and you mix it around and it looks the same throughout, that's what homogeneous means. Okay, so there's two parts of a solution. What are they, guys? Solute, solvent. Okay, let's learn about them in a little bit more detail. The solute is the substance that is dissolved in the solvent. It's the substance that gets dissolved in the solvent. And so I would put out in the margins by solute, or maybe after the definition there, it's usually the solid part. It's the solid part that gets dissolved. Okay, let's contrast that to the other part of the solution, which is the solvent. The solvent is the most plentiful substance in the solution. So it's the most plentiful, or the most numerous thing in the solution. It's called the solvent. Let's put this in the margins. Usually the solvent is water. In fact, water is known as the universal solvent. We just got done studying the polarity of different molecules. Well, water is polar. It has a slightly positive side and a slightly negative side. That helps water dissolve a lot of different compounds. Water can dissolve a lot of things. And so most of the time, your solvent is going to be water. Now, when I was going through school, it was the hardest thing for me to keep these straight. Solute and solvent. And I went to the University of Utah, and they're the Utes. Okay, so here's how I remember it, and it's helped me ever since. So I just think that solute ends in ute, and the Utes are solid because they always beat BYU, right? They're solid. So that's what helps me remember that the solute is solid. The solvent is water. Okay. So find something. If that doesn't help you, find something that will help you remember that the solute is the substance that is solid. It gets dissolved. The solvent is the water. Okay, so I've got a picture down here. This solid substance is the solute. The solvent, which is usually what? Water, will start attacking the solute, and it dissolves it. So it's attacking, it's dissolving the solute. And what you notice here is it's kind of mixed the same throughout. It's a homogeneous mixture. There's a solute and a solvent, and it's kind of mixed the same throughout. That's what a solution is. Now, most people, and including myself, when I started learning about solutions, you would always think that they're liquids, that they have to exist in the liquid phase. But that's not true. There can be solutions that exist in the gas phase and also the solid phase. Let me show you what I mean. This table here goes through and it just lists different types of solutions. So when we think of solutions, you're probably thinking of liquid, like maybe seawater, ocean water. What's the solvent in seawater? Okay, so in seawater, the most plentiful substance or the solvent in seawater is what, guys?
Water.
It's water. Okay, water. Now, what's dissolved in seawater? What is the water dissolved?
Salt.
Salt, sodium chloride. So that is your solute. Now that's what, we're pretty familiar with that. But what if I asked you this? What about Kool-Aid? What is the solute in Kool-Aid? The powder, the solid stuff, the powder that you put in. What's the solvent? It's water. And as you notice, the solvent, usually it's water. Okay, usually it's water. All right. When we think of solutions, we're usually thinking about liquids, but let me give you an example of a gas solution. In fact, the air in this room is a solution. What's the most plentiful substance in the air that you're breathing right now? Nitrogen. 70% of the air that you breathe is nitrogen. So that, by definition, is the solvent. Solute is something that's not as plentiful. So oxygen could be the solute. Could CO2 be a solute in the air? Sure, there's a lot of different solutes in the air. So oxygen would be the solute. Now, let's talk about a solution in the solid phase. A good example of this is steel. Steel is a mixture of two things. It's a mixture of the most plentiful substance in steel is iron. But to strengthen the iron, to make it into steel, you throw in a little bit of carbon. Okay, so that's your solute. So again, solutions can be in the liquid, gas, or the solid phase. Okay, there's some vocabulary terms that you're going to need to understand, because when we describe solutions, there's a lot of different ways you can describe them. So let's learn the vocabulary terms with solutions. Number one, soluble. Soluble describes a substance that can be dissolved in a given solvent. So if it can be dissolved, we say it's soluble. Let me give an example. Is sugar soluble in water? It is. Sugar can be dissolved in water. So soluble, guys, I always just think of, can it be dissolved? If it can, then it's soluble. Here's a term that we don't see very often. It's called miscible. Miscible describes two liquids that are soluble in each other. So two liquids that can be dissolved in each other, you mix them and it looks the same throughout. Here's an example. Is water and milk miscible?
Yes.
Yeah, if you put water in some milk, it still looks the same throughout, and it's going to stay mixed. It just dilutes the milk a little bit, right? And so that's an example of two miscible liquids. All right, what about insoluble? So this is the opposite of soluble. It describes a substance that can't be dissolved. So let me tell you what I mean. Is sand and water, can you dissolve sand in water? No. And you can put some sand in the water, but it's not going to dissolve. It's just going to stay at the bottom, right? And so sand is insoluble in water. So if it can't be dissolved, we say it's insoluble. And finally, the opposite of miscible is immiscible. Describes two liquids that can be mixed, but shortly after you stop mixing them, they will separate. What's an example of two immiscible solutions? Oil and water. Perfect. You can put oil in water and mix it around, and it will look like it's mixed. But what happens right when you stop mixing it? It separates again. And the oil will go to the top, and the water stays on the bottom, right? So they separate out. Okay? Very good. Okay, the rest of the lesson, though, is going to focus on solutions and talking about its concentration. Okay, the concentration of solutions. This is a very big topic in chemistry, and it's important that you learn this one. So let's start with concentration first. Concentration is a measure of how much solute is dissolved in a specific amount of solvent. Okay, you're supposed to write that definition. So again, concentration is a measure of how much solute is dissolved in the solvent. So think about Kool-Aid, since that's something we're all familiar with. If you put a whole bunch of packets in a given amount of water, say a gallon of water, what is that doing to it? Are you making it more concentrated or less concentrated? You're making it more concentrated. You're putting way more solute, in this case the sugar, in a given amount of solvent, in this case water. And so that's what we can think about. Solutions are often described qualitatively, which means not with numbers, just looking at it with your eyes, as either concentrated or dilute. So I'm going to go ahead, I've got these cups on the bottom, and I'm going to put a letter on each of them and ask you some questions. Which Kool-Aid, this is Kool-Aid, which Kool-Aid cup would you say is dilute, the most dilute? A. Now why can you say that? Yeah, it looks more clear. And we have experience with Kool-Aid. If you put a little bit in, it's still mostly like water, and you can kind of see through it. Which cup down here would be most concentrated? E. This one is most concentrated. They must have dumped a whole bunch of sugar in this one. How do we know? Well, you can't really even see through it anymore. Okay, so qualitatively just means we're just looking at it. We're not putting numbers to it. We're just looking at it. Now, is that good enough in chemistry?
No.
If I say, go make me a concentrated solution of this acid, is that good enough? No. Chemistry is a very precise science. So qualitative measurements of concentration, they're okay. But in chemistry, we're going to take it a bit farther. We want to be more precise. And so we're going to talk about how to describe concentrations in terms of quantitative measurements. Okay, so solutions can be described quantitatively. A quantity just means a number. In the following ways. Number one is the most important. Okay, so you're supposed to list them here. The first way that we describe concentration of solutions is called molarity. Molarity is given this symbol, capital M. So whenever you see that, you know it's a measurement of how concentrated the solution is. By far, this is the most common way that chemists will measure the concentration of solutions. But there's other ways too. Let's briefly go over them. Molality sounds kind of the same as molarity, but molality is given the symbol lowercase m. In fact, we're not even going to talk about number 2. It's used sparingly in chemistry. 3 and 4. Okay, let's talk about them. We'll talk about, at the end of this lesson briefly, parts per million, which is a measurement of how concentrated a solution is. ppm is how they abbreviate parts per million. And then there's parts per billion, ppb. We'll talk about that at the very end of the lesson. But what we're going to do now is focus on number 1. Okay, so by number 1, put a little star. That's the one you've got to know about. Okay, let's start with number 1, molarity. Here's the definition of molarity. It's the number of moles of solute dissolved per liter of solution. Moles of solute dissolved per liter of solution. So there's that word again. You probably thought you were done with, but here it is again. Moles. Okay? So we learned about moles in the previous 2 chapters. So we're going to use it again. Okay, it's used in this molarity. It's a way to describe the concentration of a solution. So in your guided notes here, it's got a formula for calculating molarity. I want you to write this down. Molarity, remember, has the symbol capital M. Here's how you calculate it. It's equal to the moles of solute divided by liters of solution. Moles of solute divided by liters of solution. Now, if we look at this equation, if you put a whole bunch of sugar in your Kool-Aid, you're increasing the moles of sugar, which is our solute, right? When this number gets bigger, what happens to the concentration? Well, it gets bigger. What if we put less sugar in our Kool-Aid so the moles is decreased? What is that going to do to our concentration of the Kool-Aid? Well, it's going to decrease it. Okay. But liters of solution, so how much water you use, also has an effect. We'll see that today. Before we leave this slide, I want you to write this somewhere. On all of the problems today, we're going to start this way. Molarity is equal to moles divided by liters. Let's just abbreviate that formula to there. Molarity is equal to moles divided by liters. All right, I've got an example problem. This one is in your notes, and I'm going to go through this one slow. And I want you guys to write down everything that I write down. So let's read it. It says, what is the molarity of an aqueous solution containing 40 grams of glucose, which is C6H12O6, in 1.5 liters of solution? Okay, a lot going on in one sentence. But what does it want us to find? The molarity. So circle molarity in your notes. That's what we need to find. Now let's underline what it gave us. What did it give us? What information? Good. 40 grams of glucose. What other information did it give us? It's in 1.5 liters of solution. Okay. So we always like to take the problem and circle what it's asking us to find and underline what they give us. Now, if we're asked to find molarity, what's the formula for molarity, guys? Good. Molarity is equal to the moles divided by liters. That's how we're going to start all of these problems today. Now let's use that and plug in the information that they gave us. Did it give us molarity? No, that's what we're trying to find. So I'm trying to find molarity, so I'm going to keep it as M. Did it give us moles? It didn't, but it gave us grams. Now, do we know a way to go from grams to moles? So it provided us a way to calculate the moles. Let's do that now. 40 grams of glucose, okay? Please put that over 1. Now, you can use your roadmap if you'd like to, but there's an easier way of figuring this out. You can always remember, if grams of glucose is on top, where does it got to go in order to cancel out?
Bottom.
Good. It's got to go on the bottom. And we're trying to go to 1 mole of the substance. So 1 mole of glucose is equal to how many grams of glucose? Well, this is called molar mass. It's how much mass is in 1 mole. So let's go to the periodic table because that's where we find it. What's the molar mass of carbon? 12. But how many carbon atoms do I have in a glucose molecule? 6. So I need to times that by 6. Let's go to the next element, which is hydrogen. What's its molar mass if you look on the periodic table?
1.
It's 1. But how many hydrogens do I have in the molecule?
12.
12. So I'm going to times it by 12. Now let's go to the next element, oxygen. What's the molar mass if you look at the periodic table of oxygen?
16.
16. How many oxygens do I have in the molecule?
6.
6. Okay, so if you times those through, isn't 12 times 6, what is that, 72? 1 times 12 is 12. And 16 times 6, what is that? 96? Right. Okay, now what do I do with all these numbers, guys? You add them together. And when you do that, what do you get? Yeah, exactly 180. So that tells me that there's 180 grams in 1 mole for glucose. Okay, now we've got our conversion factor. Our grams of glucose cancel out, so I'd like to see you strike those units out. And we're left with moles of glucose. Well, that's what I need to put in my formula right here. Okay, so let's just throw an equal sign. Now it's an easy math problem. 40 times 1 is 40. On the bottom, we got 1 times 180. It's 180. Okay, so now grab the calculator. 40 divided by 180 is equal to 0.2 repeating, right? Let's go to 2 decimal places. So 0.22. What are my units? Moles of glucose. Now, where do I put that in my formula? On top. So that moles number comes in on top. So I'm going to put 0.22 on top. Now, what do we got to divide it by?
1.5.
Good, the liters. And it told us we had 1.5 liters. So I'm going to put the 1.5 on the bottom. Now, if you divide 0.22 by 1.5,
0.148.
0.148. So the molarity is equal to 0.148. Now, how would a chemist write this? And here's how a chemist would write this. They would say that it is a 0.148 m for molarity, or they would say molar, concentration of glucose. We need to put the substance as well, so C6H12O6. So again, they would say 0.184 molar solution of glucose. Now you guys are starting to learn about molarity. It's a way to tell the concentration of a solution. There's kind of a rule of thumb that I go off when I'm teaching this at the beginning. So here's what I say. If the molarity is greater than 1, I say that it's a concentrated solution. And if the molarity is less than 1, I say it's a dilute solution. Now that's just a rule of thumb. It's not true of all solutions. Some solutions are really concentrated and really dangerous at lower concentrations than 1. But what would you say this solution is? Concentrated or dilute? Yeah, it's less than 1, so I would say that's a dilute solution of glucose. Not too bad, is it, guys? So just remember, start all of these problems with this formula. Molarity is equal to moles divided by liters. Okay, let's see if you got this. Practice problem number 18. It says calculate the molarity of a 1.6 liter of solution containing 1.55 grams of dissolved KBr. KBr is potassium bromide. All right, what should we do first? What are you circling? It says calculate the molarity. So I hope that you're circling molarity. What should we underline? Well, it's giving us 1.6 liters. It's also giving us 1.55 grams KBr. I always start every problem when it's about molarity with the formula. Molarity is equal to moles divided by liters. It didn't give us molarity. In fact, that's what we're supposed to find, so I'm just going to keep it as M, big M. Did it give us the moles, guys? No, but it gave us grams, so it gave us a way to convert to moles. So let's do that. 1.55 grams of this substance, potassium bromide. Put it over 1. Let's use a conversion factor and convert to moles. If grams of KBr is on bottom or on top, it's got to go on bottom in order for it to cancel out. We're trying to go to moles, so put 1 mole of KBr on top. Now the molar mass. Potassium is 39. And we have just one of them in the molecule, the compound here. And bromine, if you look on the periodic table, goes to 80. Okay, so that's 119. My grams of potassium bromide cancel out. And I'm left with moles of potassium bromide. So we can stop there. Let's throw on an equal sign. 1.55 times 1 is 1.55. 1 times 119 is 119. So all we have to do is divide it. 1.55 divided by 119. Are you guys getting this? 0.013. And my units are going to be moles of KBr. Now, is that my answer? No, that's just the moles. So that's what we're going to plug in on the top. So when I put in for moles, that's 0.013. And what do I put on the bottom?
1.6.
Yeah, the liters, it says it gave us 1.6 liters of solution. Okay, so now we're about done. We just take 0.013 and divide it by 1.6. The molarity of this solution is 0.008. Now a chemist would write it like this. They would say it's a 0.008 molar solution of KBr. You have to put the substance that's dissolved in that solution. Concentrated or dilute?
Dilute.
It's pretty dilute. Who got that right? Just by raising hands. Okay, good job. Guys, I've got one more practice problem on this sort of calculation. So on this one, 19. Practice problem number 19. I would like you guys to try this one on your own. Please give it an honest effort. Try to get the right answer. And I promise if you try it, that's where you're really going to learn it. So if you're watching the video, please hit pause and try it before you move on. Okay, so I went ahead and solved it, and I hope that you guys gave it an honest effort as well. But let me explain what I did, okay? So I read it. It's asking for molarity. We underline what's given. 9.5 grams of NaOCl and per liter of bleach. Okay, it's asking us about molarity. So I hope that you start all of these problems, guys, with molarity is equal to moles over liters. I'm asked to find molarity, so I'm just bringing the capital M down, is equal to. Now it didn't give us moles, but it gave us grams. And when you convert that to moles for this compound, this is the compound that's in bleach, you should have solved for 0.128 moles. Now when it says per liter means 1 liter. So you divide it by 1 liter. Your molarity is 0.128, and a chemist would say that is a 0.128 molar solution of NaOCl, sodium hypochlorite, which is what bleach is. Concentrated or dilute? It's dilute. It's less than 1, so by my rule of thumb, when we're beginning to learn about this, I would say that's a dilute solution of bleach. Okay. How many of you guys got it? Okay, very good. We're going to kind of switch gears a little bit and ask these kinds of questions in a different way. So let's move on. I've got, what we're going to talk about now is preparing molar solutions. So there's going to be a lab that you guys are going to do where I'm going to ask you to prepare different concentrations of Kool-Aid. And these are the kind of calculations you're going to have to do for that lab. So here we go. I've got an example problem first, and this is in the book. So I'm going to go over this problem really slow. And I want you guys to write down everything that I write down. Okay? So let's read it first of all. It says, how many grams of calcium chloride, CaCl2 is calcium chloride, would be dissolved in a 1.0 liter of a 0.1 molar solution of calcium chloride? Okay, first of all, what is it asking us for?
Grams of calcium chloride.
Yeah, it says how many grams of calcium chloride we would need to dissolve in that. Okay, what's it giving us? Well, it's giving us 1.0 liters. And what else? The 0.1 molar solution. So it's giving us the concentration. It's giving us the molarity. So this is going to be a little different. But let's start it the same way. If there's molarity involved, we know that molarity is equal to what, guys? Moles divided by liters. So always start the problems this way. And now we'll just fill in the information. Okay? Did it give us capital M? Did it give us molarity?
Yes.
It did. Yeah, this capital M means that's how concentrated it is. So 0.1 goes in for the molarity. Well, molarity is equal to moles. Did it give us moles? It didn't. So I'm going to write moles. Just write it in there. It didn't give it to us, so I don't have a number to report. Now, divided by liters. Did it give us liters? Yeah, it told us that it was a 1 liter solution. So 1 goes in at the bottom. Now, of course it's 1, so 0.1 is equal to the moles. But if this was a different number, you want to get moles by itself, we're going to times both sides by 1. It cancels out here. 1 times 0.1 is 0.1. So 0.1 is equal to the moles. Is that what it was asking us? No. It wanted to know the grams. So is there a way we could take this and go to grams? Sure. Let's use that stoichiometry and go in the opposite direction. But this is moles of calcium chloride. So we're going to start our calculations with 0.1 moles of calcium chloride. Put that over 1. Okay? And now we're going to have to use a conversion factor to convert it to grams. If moles of calcium chloride is on top, in order to get it to cancel out, we need to put it on the bottom. In 1 mole of calcium chloride, how many grams is there?
110.
Good, 110. I think that's right. Let's make sure. So if we've got calcium on the periodic table, it's 40. Okay, and in this compound, I've just got 1 of them. So times by 1. We've got chlorine. If you look on the periodic table, its molar mass is what? 35? How many chlorines do I have, though? 2. So I'm going to times that by 2, that's 70. And 40 times 1 is 40. So when you add them together, yeah, it's 110. So there's 110 grams in 1 mole. Now we're pretty much done. We're to grams of calcium chloride, which is what I wanted. So let's stop there. My moles divided by moles cancels out. So those units are gone. So all we have to do is take 0.1 times 110. If you do that in your calculator, you should get 11. 11.0. 11.0 what? Grams of calcium chloride. Okay. Very good. Who got it right? Okay, so that's how you would solve this problem. Same thing, guys. Start it with this formula here. Molarity is equal to moles over liter. Then just plug in and solve for whatever it's asking. It's that easy. Okay, I've got a couple of practice problems for you to try. Okay, actually I'll go through this one with you. So how many grams of calcium chloride should be dissolved in 500 milliliters of water to make a 0.2 molar solution of calcium chloride? Okay, first things first. What's it asking us to find? How many grams of calcium chloride again? Okay, so I circle it. If I were you in your guided notes, that's what I would circle. What should we underline? What's it giving us? Oh, 500 milliliters. And what else? 0.2 molar. So it's giving us the concentration. Okay. Now, before I start anything else, if you see milliliters, you got to pause for a second. Does that show up in our formula? Milliliters? It doesn't. How are we supposed to report volume? in liters. So I hope, guys, that you remember which way to move the decimal and how many. So if you don't, remember the metric system prefixes. Killer, hippos, die, buy, drinking, chunky, milk. If you will remember those prefixes, you will never have to wonder which way to move the decimal. Okay? So let's make boxes here. For volume, what's our base unit for volume? Isn't it the liter?
Yeah.
It's the liter. Okay? Okay, so if liters is the base unit, where are we, guys, if we're at milliliters? We're in the millibox, this M box. How many boxes do I need to go over until I hit the liters? So let's count them. 1, 2, 3. And that tells you how many times you need to move the decimal and in which direction. So if the decimal's right here, I need to move it 3 times to the left. 1, 2, 3. So before we do anything with this problem, you should see that 500 milliliters is equal to 0.5 liters. Okay, you've got to do that first. Now we can start the problem. I would always start it with this. Molarity is equal to moles divided by liters, always. Okay, now let's plug in. Did it give us molarity? The answer is yes. 0.2. This capital M tells us that's the concentration, that's the molarity. Is equal to, did it give us moles?
No.
Nope, so I'm just going to write moles. Divided by, did it give us the liters? Yeah, it said 500 milliliters, and we went ahead and converted that to 0.5 liters. So now what's my path from here? I want, ultimately, grams. The way I can get there is if I solve for moles, I can then convert the moles of calcium chloride to grams of calcium chloride. So that's where we're headed. But I need to get moles by itself. How do I get rid of this 0.5 on the bottom? Yeah, to get it off the bottom, you're going to have to times it by 0.5. Now it's an equation, so you got to do it to both sides. Over here, the reason that we times it was to get it to cancel out. It cancels out. On this side, 0.5 times 0.2, isn't that 0.1? Is equal to the moles. So we have 0.1 moles of what substance? Calcium chloride. So that's where you're going to start your stoichiometry, your calculations here. We're going to take 0.1 moles calcium chloride and put it over 1. And we're going to use a conversion factor to switch that to grams. If moles of calcium chloride is on top, we know it's got to go on the bottom. In 1 mole of calcium chloride, how many grams are there? It's the same as the previous problem, calcium chloride. So it's 110. Wasn't it 110, guys?
Yeah.
Yeah, 110 grams of calcium chloride. Now, if you look here, my moles cancel out, and I'm left with grams of calcium chloride, which is what I wanted. So we're done. 0.1 times 110. If you do that in your calculator, should get 11.0 grams of calcium chloride. There's your answer. Now, if you're observant, you'll say that's exactly the same number of grams as in the previous problem, right? How come this is the same? Well, our concentration was twice as much, but the amount of solution was cut in half. And so, in the end, it's the same amount. All right, guys, I've got one more practice problem for you, and I would like you to try this one on your own. Okay? So give it an honest effort. That's where you're really going to learn something, is when you try it on your own. So please hit pause if you're watching the video, and once you have your answer, hit play and see if you got it right. Okay, guys, so I went ahead and solved it. Hopefully you hit pause, and hopefully you were able to get this answer. 30 grams of sodium hydroxide. Okay? Go ahead, and it's asking us for mass of sodium hydroxide, so that's what I circled. It gave us 250 milliliters. Now remember, you got to move the decimal, and right here there's an understood decimal place. 3 to the left. So that becomes 0.25 liters. And then I underlined the 3.0 molarity. So it gave us the molarity. So molarity is equal to moles divided by liters. It gave us that was 3. It didn't give us moles, so I just wrote moles. It did give us the liters, 0.25. So that's why I wrote that here. Times both sides by 0.25 to get it to cancel off this side. 0.25 times 3 is 0.75, and that's equal to the moles. The substance that we're talking about is sodium hydroxide. So that's why I started this with 0.75 moles of sodium hydroxide, converted it to grams using the molar mass, and it was 30 grams. Okay, so I hope we understand what we're doing here. If you were asked, if you had a job in a chemistry lab, and your boss wanted a solution that was 3 molar sodium hydroxide, you would be able to go and figure this out. If you wanted it to be in 0.25 liters, so 250 milliliters, you would have to go and measure out 30 grams of sodium hydroxide on the scale, dump it into 250 milliliters of water, and that solution, the final solution would be at 0.3 molar concentration. All right. There's other ways besides molarity to figure out the concentration of solutions. Here's one, molality. Although chemists don't really use it all that much, I thought I would just briefly go over it. Molality is given the lowercase m. Moles of solute, that's the same, but where it's different is that it uses kilograms of solvent. So it's using the mass of the solvent instead of the volume of the solvent. That's the only thing that's different, but we're not going to go over any problems with molality. Here's something that you will see. Okay? Concentrations given in parts per million or parts per billion. So let's briefly talk about that. There's a spot in your notes for you to write this. Okay, parts per million. Abbreviation is ppm. What that is saying is it's saying that there is 1 part solute for 1 million parts solvent. So this is a very dilute unit of measurement here. It's very dilute. In fact, it's equivalent, it says here, to 1 drop of water in 50 liters, which is about the size of a fuel tank in your car. Or if you think about it in terms of time, that would only be 32 seconds out of the year. So it's not very much. It's very dilute. Well, there's another unit of concentration that's even more dilute. Parts per billion. Its abbreviation is ppb. It denotes 1 part solute for a billion parts solvent. Equivalent to about 3 seconds out of 100 years. So very, very dilute way to measure solutions. So when would you see parts per million and parts per billion? Here's an example. Cities have to give their residents a report on the water that they're drinking. The city provides the water, so they got to test it every year. And they go through and they take a sample of water and they test it for all these different elements on the periodic table. There's some that could show up. It's very difficult to get 100% pure water. Well, what they would do is report that. That report's going to say, oh, there was this many ions per parts per million or parts per billion. It's very, very dilute way to measure solutions. And that pretty much is all for the lesson today. I hope that you now understand solutions a little bit better, especially how to take the concentration in terms of the molarity. There's going to be a lot of molarity calculations that you're going to have to do. So to give you some more practice with calculating molarity, I want you to get your student workbooks and let's go to the molarity worksheet. Again, it's called Molarity Worksheet. Please get that done, and I hope that it makes sense, and I hope that this video helped.